Excellent. So for part 2 of our 3 easy pieces, we're going to try to find a Laplace transform of the exponentially decreasing step function. This is one of the most important identities for solving ODEs. Okay, so what does that look like? So let's plot it. So if we start out with the step function right there, nothing happens prior to t equals 0, and anything happens after t equals 0 is just a quick exponential decreasing envelope. Cool. So let's just do this. So the Laplace transform of f of t is the doubly infinite integral f of t e to the minus st dt. And as before, a large portion on the left is going to be 0. So now we can just write this integral as from 0 to infinity e to the negative alpha t times e to the negative st dt. So now it's just a matter of calculus. So this integral becomes Laplace transform of f of t is now the integral from 0 to infinity e to the minus s plus alpha t, because exponents add. Okay, so then you integrate, you're going to get 1 over s plus alpha, the negative of that, times e to the minus s plus alpha t with the integrands. And as before, the improper integrand means you're going to have the limit as t approaches infinity e to the minus s plus alpha t minus the second term with 0 right there plugged into it. Okay, so that means that term is just 1. So now, just like before, if s was a complex number, sigma plus j omega, we can rewrite the entire expression as the following. So it's going to be the limit as t approaches infinity e to the minus sigma plus j omega plus alpha t minus 1. Okay, the thing to note here is sigma and alpha are actually real numbers. So we can actually group them together into one pot. So to do that, we're going to write the Laplace transform equals 1 over s plus alpha, negative that, times t approaching infinity for the limit, where we have an exponential decrease term in blue times an Euler term, minus 1. So the Euler term, we know they're just waves. Now the blue part here must be the exponential envelope. Cool. So now the question is, when is that limit finite? And like before, we really want a decreasing exponential envelope. And that means the exponential term, sigma plus alpha, it better be a positive number. Cool. Alright, so now also we know that since real part of s is sigma, we can rewrite this expression as real part of s plus alpha is greater than 0, which hence means real of s is greater than negative alpha. So this would be a region of convergence for a final answer. Okay, so again, that ensures our limit will go to 0 or finite as t approaches infinity. So with all that fact in mind, what we're going to do now is our Laplace transform equals the following. Well, first, we're going to just copy that equation right there. So Laplace transform of f of t equals negative 1 over s plus alpha times, now the limit with all these facts, that limit is going to be 0. And then minus 1 at the end. Great. That means the complete solution, which is the Laplace transform of an exponentially decreasing step function, is now equal to 1 over s plus alpha, which is the decaying constant. Dude, that's just the answer. Alright. So we should include ROC in our discussion. And moreover, we see that a exponential time decay in a time domain corresponds to an s shift in the s domain.